Good morning, all. Now we are going to discuss um, field effect transistor and MOSFET that is related to semiconductor devices in the fourth chapter. The name is field effect transistor and MOSFET. So already in previous videos we have learned about the transistor, PN junction diode and rectifiers, filters and regulated power supply. In this video we have discussed about the field effect transistor and MOSFET. So the first one is field effect transistor. So in 1945, Shockley has an idea for making a solid state device out of semiconductors. That means, so in 1995, the name of this scientist is Shockley. He gave an idea for making a solid state device out of semiconductors. He reasoned that a strong electrical field could cause the flow of electricity within a nearby semiconductor. He reasoned that a strong electrical field would cause the flow of electricity within a nearby semiconductor. He tried to build one, but it did not work. 3 years later, Raytheon and Burden built the first working transistor, the germanium point contact transistor, which was designed as the junction transistor or a sandwich transistor. In 1960s, Bell scientist John Butler developed a new design based on Shockley's original field effect theories. So by the late 1960s, manufacturers converted from the junction type integrated to the semiconductors. So that means that is the history of the transistor. That means already it will start the invention of 1945 solid state device from the semiconductor. After that, in 1960s, Bell scientist John Atlanta developed a new designated on Shockley's original field effect theories. That means from these theories we can get the in 1960s we can get the field effect transistor and transistors. So now here we go for the field effect transistor. It is also short name as FET, F-E-T. F for field effect transistor. It is also known as a junction field effect transistor. So the field effect devices are those in which current is controlled by the action of an electric field rather than carrier injection. So in case of transistor, so the current flowing through the device is due to the either majority carriers or a majority carriers. That means those majority carriers are either electrons or holes. That means the current flowing through the device within a transistor is due to carriers. But in case of FET, the field effect devices are those in which current is controlled. The current is controlled by the action of an electric field rather than carrier injection. So that means in case of field effect devices, the current will be controlled by the action of an electric field rather than the carrier injection. So the field effect transistors are so named because a weak electrical signal coming in through one electrode creates an electric field through the rest of the transistor. That means, so field effect transistors are so named. Why we are called as field effect transistor means a weak electrical signal coming in through one electrode. That means weak electrical signal passes through the one electrode which will create an electric field through the rest of the transistor. That means weak signal will be passes through the electrode. This electrode will create the electric field through the rest of the transistor. The FET was known as a unipolar transistor. The term refers to the fact that current is transported by carrier of one polarity, majority, whereas in the conventional bipolar transistor, carriers of both polarities, majority and minority, are involved. That means in case of FET, that is field effect transistor, it is also known as unipolar. Why we are calling unipolar means So the current conduction is due to only majority carriers. So that's why the FET will be called as unipolar transistor. But in conventional transistor, the current conduction is due to both majority and minority carriers. So that's why the FET is also called as a unipolar transistor. At the same time, the current will be controlled by the action of an electric field. So rather than the carrier injection. That means in case of transistor, the current conduction is due to the both majority and minority carriers. But in this case, the current conduction will be controlled by the action of an electric field. Now the field effect transistor families here we have discussed. So the family of FET devices may be divided into junction FET and depletion mode MOSFET, enhancement mode MOSFET. That means the family of these FET devices are junction field effect transistor, depletion mode metal oxide semiconductor field effect transistor, at the same time enhancement mode MOSFET. These are the families of FET. So now first we are going to discuss about the junction FETs, junction field effect transistors. It is simply known as JFETs. So these JFETs consist of a piece of high sensitivity, consists of a piece of high resistivity semiconductor material, usually silicon, which constitutes a channel for a majority carrier flow. That means in this JFET, which consists of a piece of high resistivity semiconductor material. So that means in FET also we are using the semiconductors. So the semiconductor type is equal to mostly we are using silicon, which constitutes a channel. This silicon will be having high resistivity. This silicon will act as a channel for the majority carrier flow. For carrier flow, we make a channel. That channel will be made by the silicon. So conducting semiconductor channel between two ohmic contacts, that is source and drain. So look at the picture. So these are the symbols of junction field effect transistor. So these junction field effect transistor having two types, that is N channel JFET and P channel JFET. So that means here is equal to. So in case of N channel, the current direction is into the transistor. In case of P channel, out from the transistor, that is from the gate terminal. The majority carriers are enter into the device. Here the majority carriers are leaving from the device. These are the two types of junction transistor, that is N channel JFET and P channel JFET. So N channel, that means we call it as channel. This channel will be made by the semiconductor. That semiconductor will be equal to silicon. So this channel will be used to flow the majority of carriers through it. This channel will be used as a majority carrier flow. So now here, so this is the diagram for basic structure of the N channel or otherwise JFET, N channel JFET. Here you can consider, first you can take a one substrate. This total will be equal to our substrate. So this substrate having, again this FET having the three terminals just like a transistor. So gate, source and drain, these are the three terminals in the FET. In case of transistor, there is a emitter, base and collector. In similar manner, the source. So in case of BJT, this is emitter. In case of FET, source. That means the source will allow the majority carriers. Base will be equal to here gate. Collector will be equal to drain. These are the three terminals in case of FET. So in this case, we are creating one channel in channel. This channel will be acts as a majority carrier flow. So this total will be within a substrate. So here we go for the N channel. So that's why the substrate will be equal to the N type of substrate. Here we can use. So the basic structure, this is the basic structure of a FET. Now so the face look like this, that is source, drain and gate. These are the three terminals. So here we are using the cross sectional view of a transistor, that is FET. So we can create, so drain, gate and source. Okay, so in between, that means, so here we can create a channel. This channel is from source to the drain, that is the majority carriers will be flowing from source to the drain. So next, this channel will be equal to, this will be called as, the remaining space will be called as a substrate. So this will be equal to, that means the metal contacts, the silver color will be indicates the metal contacts of the three terminals. Those three terminals are drain, gate and source. So here this will be equal to, the red color will be indicates the p type substrate. Substrate type is here is equal to the p type substrate. This is the cross sectional view of n channel. So in case of n channel FET, so mainly we can broadly having this red color mark or indication will indicate the substrate. Again the channel is from source to the drain, which will be used to the flow of majority charge carriers. Next, the metallic contacts will be used for contacting the three terminals. Those three terminals are drain, gate and source. So this is the standard symbol of a FET. So the inward direction of arrow mark will indicate the N channel JFET. This is the basic structure and cross-sectional view of a N-channel FET. So these JFET having some of the parameters, that is the JFET is a high input resistance device while the BJT is comparatively low. So when comparing with the BJT with JFET, so this JFET having high input resistance. So if the channel is doped with a donor impurity, which makes n-type metal is formed, and the channel current will consist of electrons depending upon the doping. So we are dope the channel with the donor impurities, that is pentavalent elements. So then which makes the n-type channel, n-type material or n-type JFET. And the channel current will consist of electrons, because n-type means the majority carriers are electrons. So that's why the channel current will consist of electrons. That means depending upon the doping impurities. Suppose when you are doped the channel with donor impurities, which makes the n-type FET. So suppose if the channel is doped with an acceptor impurity, that means trivalent elements, which makes the p-type material will be formed, and the channel current will consist of holes. So these n-channel devices have greater conductivity than p-channel types, since electrons have higher mobility than the holes. Thus the n-channel JFETs are approximately twice as efficient conductors compared to their p-channel counterparts. When we are comparing the n-channel and p-channel, so the conductivity of the n-channel devices will be greater than the p-channel, because so these n-channel having the electrons, majority carriers are electrons. So these electrons having the higher mobility, due to that, so which having the greater conductivity. So that's why the efficiency approximately twice as efficient conductors comparing to their p-channel counterparts. So here the magnitude of this current is controlled by a voltage applied to a gate, which is a reverse biased. Here the flow of current through the device will be, that is the magnitude of this current will be controlled by a voltage applied to the gate. So this gate will be connected in a reverse bias. The fundamental difference between JFET and BJT devices are, when the JFET junction is reverse biased, the gate current is practically zero, whereas the base current of the BJT is always some value greater than 0. So due to the reverse bias of the gate, so the gate current will be equal to 0. Practically the gate current will be 0, but in case of BJT, so we make the base as a forward bias. So that's why the base current having the some value, that value is greater than 0. So already we go for learn about basic structure and the symbol of a trans FET, symbol of a FET. Okay, so this is the differences between JFET and BJT. So JFET is also called as a unipolar transistor because so the conduction is due to majority carriers only. But in case of BJT, it will take the conduction due to both majority and minority carriers. That's why BJT will be called as bipolar junction transistor. FET will be called as a unipolar. At the same time, comparing the input impedance or input resistance of a JFET with BJT, so the input impedance of the JFET is higher than the BJT because so in case of JFET, so the gate terminal will be the gate will be connected in reverse biased. Due to reverse bias, the gate current will be zero. So that's why which is having high input impedance than the BJT. At the same time, so in case of BJT, we can call the three terminals as emitter, base and collector. But in case of FET, it will be equal to gate, source and drain. So it will be the types of JFETs are N channel or a P channel. Here the mostly we can create the channel. So this channel will be doped with either donor impurities or acceptor impurities. When we are doped with donor impurities, it will be called as so N-type channel or N-type JFET. When we are doping the channel with acceptor impurities, it will be called as P-type transistor. When we are comparing N-type and P-type, okay, so the efficient one is equal to the N channel because so the electrons having the higher mobility. So due to the reverse bias of the gate, the gate current will be equal to 0. But in case of BJT, so the base current will be greater than 0. So now the basic structure of JFETs. So in addition to the channel, a JFET contains two ohmic contacts, the source and the drain. Okay, so here the basic structure of the JFETs. So you can create a channel for flow of majority carriers. So that will be called as a channel. Along with channel, there is a two ohmic contacts. That ohmic two contacts are source and the drain. So the JFET will conduct current equally well in either direction, and the source and drain leads are usually interchangeable. That means here the two terminal source and drain can be interchangeable. That is possible in case of low frequency applications. So that's why the conduction current, JFET will conduct the current equally well in either direction. That is from either source to the drain or from the drain, or you can interchange the drain and source terminal. It is also possible for the conduction of current. So this will be mainly possible in case of low frequency applications. So these are the basic structure and cross-sectional view of the junction field effect transistor, that is N channel, with the two P plus regions are electrically connected. So the symbol at the same time depletion region of N channel. So now go for the basic structure. So here we can use this is the circuit symbol of a N channel JFET because the arrow mark at the gate will be inward direction. So that's why it will be called as a N channel. This will be equal to symbol of N channel JFET. So next, here the basic structure. So in this basic structure, we will go for the three terminals again, that is gate, source and drain. So in this we call it as N channel. So that's why the channel here is equal to N channel. Okay, we'll go for the P plus, that is P plus region means heavily doped region. So next, so this blue color will indicate the depletion region. The blue color will indicate the depletion region. So above the depletion region, it will be equal to the N channel. So the majority carriers will be moving from source to the drain via a channel. Next, go for the cross sectional view of this transistor. So in this cross sectional view, okay, so we can consider the heavily doped P plus region. Again in between we can consider the N channel. Okay, so the thickness of the channel will be changed based on the applied voltage. So again the three terminals are here: gate, source and drain. So this is equal to the cross sectional diagram of the N channel. So next, so in this case, so we can consider for N channel, we can go for the P-type substrate. Again, we can create the N channel is in between source to the drain. So next we can provide the silicon dioxide layer for ionization. So next above that we can create the ohmic contacts. From this ohmic contact we can maintain the three terminals. Those are equal to source, gate and drain. Okay, is it clear? So that means this blue color will be indicate P-type substrate, because here we can create the N channel. So that's we can take it as P-type substrate. But we can provide the channel. So N-type. So N-type JFET. So that's why the channel name is equal to the N channel. So above that we can provide the silicon dioxide layer, that is insulation layer. So above we can provide the ohmic contacts. From this ohmic contacts we got the terminals. Those terminals are source, gate and drain. This is the cross-sectional view of a N channel. In the same manner we go for the P channel. So in case of P channel, so here instead of, so in case of P channel means we can consider the N-type substrate and the channel will be equal to P. That is the channel type is equal to the P-type channel. So remaining will be same, that is equal to the ohmic contacts. So first we can consider the P-type substrate. Above we can, in case of P channel we can go for the substrate equal to the N-type substrate. So above which we can create a P channel. So upon we can provide the insulation layer, that will be equal to the silicon dioxide layer. So above that we can provide the ohmic contacts. From these ohmic contacts we can get the three terminals. Those will be equal to the gate, drain and source. So N channel and P channel both are similar, but only the difference occur here is equal to the channel type. Now we go for briefly study of N channel JFET. So this transistor is made by forming a channel of N-type material in a P-type substrate. That means you can consider P-type substrate. So in that we can provide the N-type material as a channel. So three wires are then connected to the device. So one at each end of the channel, one connected to the substrate. So here equal to three wires. Three wires means, so two will be connected to the channel, one will be connected to the substrate. Substrate means here the substrate type is equal to the P type. So the P type substrate will be connected, the terminal is gate. So the channel connected will be equal to the source and drain. So this transistor is made by forming a channel of N-type material in a P-type substrate. Three wires are then connected to the device, one at each end of the channel, one connected to the substrate. In a sense, the device is a bit like a PN junction diode, except that there are two wires connected to the N-type side. Okay, so this formation is just like a PN junction diode, but the only except that there are two wires connected to the N-type side. That is, the channel will be connected to the two wires. So now the function of this JFET. So the gate is connected to the source. The gate will be connected to the source. Since the PN junction is reverse biased, little current will be flowing in the gate connection. So here the gate is connected to the source. So the gate terminal will be connected to this gate terminal will be connected to the source. So due to the connection of this gate to the source, which will form a PN junction. So this PN junction means here the channel is equal to the N-type channel. Gate will be equal to P. P means positive, N for negative. That is positive charge and negative charge. When we are connecting these two, which will form a PN junction, this PN junction will be in the form of a reverse biased. So due to the reverse bias, there is a little current will be flowing in the gate connection. So that's why the gate having only little amount of the current will be flowing through it. Now the potential gradient established will form a depletion layer where almost all the electrons present in the n-type channel will be swept away. So that's why due to the little amount of current will be flowing through the gate, it will provide the potential gradient. Okay, so this will provide the potential gradient established will form a depletion layer. Okay, so here is equal to our depletion layer. Depletion layer will be formed due to the little amount of the current will be flowing through the gate. So where almost all the electrons present in the n-type channel will be swept away. So from this depletion layer, the electrons will be moving towards the drain. Okay, so now, so the most depleted portion is in the half field between the gate and the drain. Half field between the gate and drain, and the least depleted area is in between gate and source. Okay, so due to the little amount of the current flowing through the gate, which will provide the potential gradient, so this gradient will be, that is, high field between gate and drain, high field between gate and drain, that is high potential gradient at drain and gate, and least potential gradient is in between source and the gate, source and the gate. So because the flow of current along the channel from the drain to the source, a flow of current from the source to the drain. So that means here, due to this potential gradient, the carriers are moving from, that is majority carriers are moving from source to the drain, but the current conventional current direction is from drain to the source. That means due to the high potential gradient, we can get, so the electrons are moving within a channel is from source to the drain, but the conventional current direction is from drain to the source. So now here we can connect the one VDD. That means, so here we can connect the source and drain. That means, so the voltage will be applied in between source and drain. That is VDS is greater than VB. Here VB is equal to the pinch of voltage. So then that means, so the remaining current known as the IDSS current will be shorted to the source. That means when increasing the drain voltage, the current will be increases to up to maximum value. The maximum current will be called as IDSS, drain to source current. Okay, we are connecting the or short circuiting the source and drain. So when we are increasing the VDSS, so when we are connecting the drain and source with some voltage supply, so when we are increases the VDS voltage, that means the supply voltage will be increases, so which increases the flow of current through the channel. So this current will be increases up to the maximum value. That maximum will be called as IDSS, that is drain current is from source to the substrate. So look at the characteristics of these N-channel FET. So the output characteristics of the N-channel JFET with the gate short circuited to the source. That means the first case here is when you are short circuiting the gate and source, there is a little amount of the current will be flowing through the gate. So that's why the output characteristics of this N-channel JFET with the gate short circuited to the source. So the initial rise in ID is related to the buildup of the depletion layer as VDS increases. So now when we are increasing the VDS is going to be increases, then ID will be slowly increases. That means which builds up a depletion layer which will increases the ID slowly. So now the curve approaches the level of the limiting current, that is IDSS, when ID begins to be pinch off. So when ID reaches the pinch off region, which will be approaches the level of limiting current, that is IDSS. So the physical meaning of this term leads to one definition of pinch off voltage Vp, which is the value of VDS at which the maximum IDSS flows. So here the pinch off voltage will be called as, so where the VDS will be equal to Vp, at this point we can get the maximum current, that will be called as IDSS. So now go for the graph here. So when you draw the output characteristics is in between VDS and ID. Okay. So when VDS will be increases slowly, the ID also increases slowly. So this region will be called as ohmic region. That means, so there is a linear relationship between VDS and ID. So that's why this region will be called as ohmic region. So once it reaches the VP. VP means pinch off voltage. That means when VDS equal to VP. So at this point we can get the maximum current to the device. That current will be called as IDSS. So beyond this point, when we are increasing the VDS, then IDSS will maintain constant. That constant region will be called as saturation region. Okay, so that means here VGS equal to 0. That means when gate and source will be short circuited, when VGS and gate and source will be short circuited, when we are increasing the VDS, there is an increasing in the ID. So when it is reached to the maximum means when it reaches the pinch off point. So when it reaches the pinch off point, we can get the maximum current, that will be called as IDSS. So beyond this pinch off point, we are increasing VDS continuously. So there is no change in the ID. That means the ID will be maintained constant at its maximum value. So this constant region will be called as saturation region. So with a steady gate source voltage of 1 volt, there is always 1 volt across the wall of the channel at the source end. That means, so we can connect the 1 volt gate voltage at the source end. A drain source voltage of 1 volt means that there will be a 2 volts across the wall at the drain end. So that means simply, so for different values of VGS, you can draw the output characteristics of JFET. So for steady gate source voltage is equal to 1 volt. So then the at the wall end the potential difference will be equal to the 2 volts, because the drain source voltage is 1 volt and the gate source will be equal to the 1 volt. So that means at the wall end we can get the 2 volts. The higher the voltage difference at the drain end means that the electron channel is squeezed down at a bit more at this end. So when you are increasing the VDS will be increases, then so the potential difference will be increased, the current flow along this channel will be increased. So this will be equal to our N channel JFET. So briefly, N channel JFET means we can consider P type substrate, we can make a N channel. So this upon this N channel we can draw the two terminals, one is drain and source. At P type substrate we brought another terminal, that will be called as gate. So these are the three terminals will be connected, gate, source and drain. So these gate, source and drain. So in case of N channel, drain and source will be connected to the N channel. Again the substrate will be connected another terminal, that will be called as gate. So the output characteristics of this N channel is, so when gate to source will be short circuited, then VDS will be increases. Short circuited means VGS equal to 0. Then VDS will be increases. There is a linear increasing in ID up to some pinch of voltage. After the pinch of voltage, when we are increasing the VDS, which maintains the maximum current as a constant. So this constant region will be called as saturation region. So when there is a linear increment between VDS and ID, is called as a ohmic region. This is about the N channel. So in the same manner, we go for the P channel. So just we can interchange the substrate and channel. In case of P channel or P type JFET, the substrate equal to the N and the channel will be equal to the P type. This is the input and output characteristics of N channel and P channel. So next video we go for the complete VI characteristics of input and output characteristics, transfer characteristics and drain characteristics of JFET. Thank you.